Hi, and welcome to this next video on the integration section from the Year 2 part course. And we've been through the big techniques of integration, which is reversing the chain rule, such as integration by inspection. We've been through integration by parts, integration by substitution. There's a couple of little bits and pieces left over that we need to deal with, and those are these. So we've got to look at how we can use integration to solve differential equations. So that'll be technically something that's new, although it's not new. So we'll see that in a second. And also we've got to be able to integrate parametric equations. So the first video is just going to deal with the differential equations, and then a different video will deal with the parametrics. Okay, on we go. So differential equations. Now that might be something that's new to you, expressed differently, but it is something you've seen before, and you've actually really been working with differentials since right at the beginning of the course, because something like that is a differential equation. So it's an equation that's expressed as a rate, in this case a change in y over change in x that pertains to a gradient. And you know that if you've got dy dx equals 2x minus 3, basically you just have to integrate to get back to the y equals, to get back to the equation of the line, and that's something you were doing in year 1. So we've got dy dx equals 2x minus 3, so that means y is going to be the integral of 2x minus 3, and so you end up with x squared minus 3x plus c. And hopefully that's all nice and straightforward and stuff you're familiar with. What I'm going to do is basically do that again, but just slightly change how we look at what we're doing. So we're going to solve this one again, but this time we're going to view it as solving a differential equation. We're going to end up with the same result, but what we're going to do is separate out the variables. The variables I've got here are y, and the only thing in terms of y is the dy part, and then I've got x's. So what I'm going to do is take this dx essentially over to the other side, so I've got my y variables on the left hand side, and my x variables on the right hand side. And so now what we're going to do is to solve this equation. You know, when you solve any equation, just do the same throughout the entire equation. So what I'm going to do is integrate both sides of the equation. So on the left, I'm integrating here with respect to y. That's what the dy part tells. And I've put this 1 here. I don't really need it, but I'll just put that there so you can see what it is that we're going to be doing. And over on this side, we're integrating with respect to x. So if I integrate 1 with respect to y, I get y. I integrate 2x minus 3 with respect to x, I get x squared minus 3x, and then I've got the plus c. Now, the interesting with the plus c is, technically speaking, when I integrate, if I integrate on the left-hand side, we should have a constant here. I integrate on the right-hand side, constant here. But essentially, it's a constant, it's just a value, so there's no point including 2 of them and having them as separate. We can just include it as one value. So I generally tend to include it on that right hand side there. As long as it's in there, then that's all we need, and you see we've got exactly the same result. So it's what you already know, but it's this idea of separating the variables, this first step here, that's the new bit. And that's the key bit to some of the equations we're going to be looking at. Because in a lot of cases, you haven't necessarily got things expressed as y equals. So let's have a look at an example. This one is going to look a lot more complicated than what we've just done, but the principles are exactly the same. So standard result here, we've got liquid cooling in a cup. There's my cup of tea. And we've got to show that at time t, the temperature is given by that equation a e to the minus kt. So it's an exponential relationship. We've got a cup of tea cooling, and we're told it cools, and the rate at which it cools is proportional to its temperature. So what we're going to do is set up a differential equation originally, and then we're going to solve it to create this equation here. So here we go. So there's my differential equation. So we're saying the rate at which the cup of tea cools, change in temperature over change in time, is proportional to the temperature. And again, that's just your basic proportional relationship that you will have seen from GCSE. We've got the constant of proportionality, this value of k. In this particular case, I've got a negative because it's decreasing, and there you go, theta represents the temperature. So the rate at which it cools is proportional to the temperature. What we've got to do now is solve that equation. So we've got to get it, instead of just being d theta, dt, we've got to get it in terms of just theta and t. So what we're going to do is, same trick as before, we're going to separate the variables. So I've got d theta here on this left-hand side, so I'm going to move the theta over to there, and I'm going to take the dt's over to the right, so we end up with that. It doesn't really matter where this k goes, because it's just a constant, at this point in time, I'm just going to leave it as a constant there on the right hand side. So we've separated the variables. Now we've got to do the integrating. So I tend just to kind of stick two integral signs in there. And so this is 1 over theta d theta, which becomes ln theta. And here we go, there's the minus kt, and there's the plus c, again remembering our constant of integration. Now, what we've got to do now is tidy that up, and we've got to get it saying theta equals, and hopefully when we take this log equation here, we're going to turn it into this equation here when it says theta equals. So we've essentially got to get the theta out of the log somehow. And the way to do that is just reverse the logs. So we've got theta equals e to the power minus kt plus c. Now we're going to use a little bit of log laws because we've got our addition within the power here. So we can rephrase this one as being e to the power kt times by e to the power c, because you know when you're adding the powers it's a multiplier. And this thing I've circled here, e to the power c, e is a fixed value, c is our constant. So this thing here is just a number, so what I'm going to do is I'm just going to recall that thing, I'm just going to call that a. And straight away, there you go, there's the format that was asked for in the question. So what we've done is started off with a setup that was expressed in terms of a rate, the rate being proportional to the rate at which the t equals is proportional to its temperature. And now what that's done is link together temperature here and time. Right, so there's our part 1 done, there's our initial equation sorted, so let's now use it in part 2. So we've got two variables we've got two constants in here. We've got this a, this is just a constant, and we've got k, which is a constant. So what we've got to do is do some working out to try and find out what those two things are. And we've got two pieces of information. The first piece of information is the initial temperature of the liquid is 80 degrees C, and the second piece of information is after 5 minutes its temperature is 50. So let's use those two things. So when t equals 0, the initial temperature is 80. So let's put those things in. We get that. So if t equals 0, this entire power becomes 0. E to the power of 0 is 1, so that just leads us to our constant a has got a value of 80. So that's that bit done. And then when t equals 5, after 5 minutes, the temperature of the cup of tea is 50 degrees Celsius. So here we go. So there's our new equation with 80 instead of a. Put in the values we just referred to. We've now got to make that say k equals. So let's do a bit of kind of dividing. So we've taken the 80 over the other side and we've got 5/8. Now let's turn that into a ln equation. So there we go. We've got minus 5k is ln 5/8. And therefore k is 1/5 ln 5/8. So minus 1/5 ln 5/8. And I'm going to write that as a decimal. There it is, 0.094. So we've got a value for k, we've got a value for a. There's our equation, our link between time and temperature. And it says find how long it takes for the liquid to fall to 40 degrees C. So now let's just put in our temperature of 40 degrees C. So when theta equals 40, in it goes. Do the working out. And again, now we've just got to find our value for t. So turn it back into the ln equation and then just do the divide by minus 0.094. And there we go. We've got t equals 3.737 minutes. That's our value for t, but it does say to the nearest second. This pops up quite a bit in exam questions. So we've got that bit of extra work to do where what we've got to do is just take the 3739 times just that bit by 60 to turn it to seconds. And there you go. You've got t is 7 minutes and 22 seconds. So that's one practical or contextual example of solving a differential equation. Let's now put it into a context of a curve, in this case an ellipse. Now you don't have to know about the format for an ellipse, you only have to do with circles on the A-level course, but we've got this example here as an ellipse just set up as a differential equation already, so that means it's just a case of solving that, so that means it could be something that pops up on your exam. The fact it's ellipse is kind of irrelevant. Let's just look at this thing here and deal with that. So we've got the gradient function for this curve is minus 25x over 4y, and we've got a point on the line, and so what we're going to do is get back and work out what the equation of that line is, and we're going to write it in this form here. Right, so on we go. Let's start off with our equation. Let's do the integrating. To do that, we've got to do the separating of the variables. There we go. So I've taken the 4y over to the left, I've taken the dx over to the right. Now we can integrate. Integral of 4y is going to be 2y squared, and integral of minus 25x is going to be minus 25 over 2x squared, and remembering our constant of integration. Now we've got the point on the curve, so this is the piece of information that's going to allow us to find the value of c. So let's put those in. So at 210 we've got that, so 10 squared is 100, 2 squared is 4. That allows us to work out c, so we've got a value of c that is 250. So there's my equation as it looks at the moment, and the final thing I've got to do with this is get it to look like that, which is your standard equation for standard form for the equation of an ellipse. A, B and C belonging to the natural numbers, so these need to be whole numbers. So what we'll do is just do a bit of tidying up to begin with. So I've brought the 25 over to x squared over to the left hand side, and now I just need to deal with the coefficients within here. We've got x squared and y squared on their own on the top, so the first thing I'm going to do is divide the entire equation by 25, and then finally deal with this, the 2 here, so divide the equation by 2, and there we go. There's our format, or there's our equation as we're being asked for. So there you go. So we've gone from a gradient function, and we've now got the equation of the ellipse. Right, on we go. Last question. This one is more like an exam style question. So we've got a partial fraction to deal with to begin with, and then it says hence. So what we're going to do is use what we got from part A to help us deal with what's going on in part B, where we've got some trig functions and a whole bunch of other nasties going on. So here we go. Let's do part A, the partial fractions bit. I'm going to go through this fairly swiftly because I'm hoping that partial fractions is something that you're familiar with. So let's just set up difference of two squares. That's where we're getting our two factors on the bottom. There's our standard format for when we're doing a partial fraction. And so let's just deal with that. So that x equals 2 gives us a value of a equals a half. X equals minus 2 gives us a value of b equals a half as well. And so there's the final result. There's our fraction written as the sum of two other fractions. Now you do tend to find that partial fractions tends not to be a topic in its own right. It does tend to pop up in amongst other stuff, as it has done in this question. Right, if you need to pause the video just to kind of make sure you're happy with everything I've done there, then please do. But if you're thinking, you know, that's all right, I'm confident with partial fractions, then let's just crack straight on. And here we go. So on we go to part B. It says hence obtain the solution of 2 cot x dy dx equals 4 minus y squared. And so there's our differential equation that we're attempting to solve. So to solve a differential equation, we're going to start off by separating the variables. So in this particular case, I'm going to bring my 4 minus y squared over to the left and take the cot x over to the right. And there we go. So there you can see there's the 2 over 4 minus y squared that we had from part A appearing there. On the right hand side, we've got, well, when this cot comes over here, it divides, it becomes 1 over cot, which makes it tan. So let's replace the fraction on the left hand side with our result from part A and do a bit of integrating. So I've put integral symbols in there as well. What I've done this one, because we've got 1 over 2 here, we've got 1 over 2 here, so I've essentially just taken that half outside the integral as is my one. So now we're going to do some integrating. So we've got to integrate 1 over 2 minus y. Hopefully we're happy with it. That's going to become a ln. That's going to become a ln. Integral of tan, it might be one that you know, can remember. If it's not, then it is in the formula booklet. So when we integrate, we've got over here, we've got a minus because it's coming from 2 minus y. That's why that's got a minus there. Ln 2 minus y. Here we've got half ln 2 plus y. And integral of tan is sec squared. Right, so that's kind of good news because we want to write the form sec squared x equals. So we've got the sec squared there. So that's looking good. We've got this plus c that we've got to figure out. So let's figure out how we're going to do that. It's going to come from here, and what I've done is just a little bit of tidying up of the lns on this the left hand side. So you can see where that's come from because we've got this minus here, which means we've got a divide. Sticking my values at y equals 0, x equals pi over 3. So let's plug those in. So what we've got on the left hand side is ln 1, which is 0. And on the right hand side, sec squared pi over 3, which if you work that out is cos pi over 3, and then invert it, square it. What we end up with is that, 0 equals 4 plus c. So clearly we've got c equals minus 4. And so then for the last thing to do is to put that minus 4 back into my equation here, and I want it sec squared equals, so I'm going to move the minus 4 over to the other side. It's going to become a plus, so that's why we've got a plus 4 there. And there you go. There's the format of the equation that was being asked for. So we've got sec squared x equals, and this thing here, this is our function of y. Right. Final example. So another exam style question that we're going to have a look at. And this one, there's quite a lot going on here. It's quite an involved question. So what we've got is we've got a cylindrical tank. We've got water flowing into the tank at a constant rate of 0.48 pi meters cubed per minute. And we've got the depth of the tank is h. And also, as well as water running in here, we've got water running out at a rate there. So we've got to take that into account. Now it says, show that t minutes after the tap has been opened, that's our depth in the of water in the tank. Okay, and then part B, we've got to find the value of t when the height of the water is when we've got 0.5 meters of depth of water in the tank. Okay, so this whole question is to do with rates, and if you think back to the work we did when we did differentiation and connected rates, that's what's going here. That's what's going to allow us to set up this differential equation. So let's think about what rates we've got going on. We've got the rate at which the water flows into the tank. So that's going to be our change in volume over change in time. And we've got water flowing in, which is the 0.48 pi. We've got water flowing out, which is the 0.6 pi h. And what's happening there is the water flowing in is happening at a constant rate, whereas the water flowing out, the rate at which it flows out will depend on how much water is in the tank. That's what this thing here is doing there. So that's our dv dt. So let's just pop that to one side for a second. Let's think about what else we've got. We're going to need dh dt. We're going to have to connect it via dv dt somehow. So let's work out the rate at which the volume changes compared to the height. So that would be dv dh. And so that one there is going to come from our formula there for the volume. And bear in mind we've got a fixed radius, so in this particular case r is a constant. So our volume is the formula that's v equals 9 pi h, and so if we differentiate that, we're going to get dv dh, which is 9 pi. So that's that rate sorted. And again, let's just pop that up there out of the way, and let's have a think about the other one that we're going to need, which is the dh dt, which is how is the height changing compared to the time. So that's that one, and that's the thing that we're going to try and find out. We haven't got anything else we can do with that at the moment. So those are our three rates. And so what we're going to do now is try and connect those things together using chain rule. So there it is. So we've got dv dh times by dh dt is dv dt, and it's the dh's here that are going to cancel out. So dh on the top, dh on the bottom, leaving us dv dt, which is what we've got there. So there's our chain rule. So let's now put those bits together. So we've got dv dh, which is the 9 pi. We've got dh dt equals dv dt, and there we go. Now, what we've got to do now is take this thing here and turn it into the expression that's being asked for, which is this bit up here. It hasn't got any decimals in it, and pi isn't there, so if you look, we've got pi appearing in all three bits, so the first thing we can do is get rid of those. And then, essentially, that's now in the format that I want, but I'm thinking, well, you know, I've got to turn, essentially, this 9 here has got to become 75, so what have I got to do to turn that into 75? Well, the answer to that is times it by 25 over 3, and if you times the whole equation by 25 over 3, lo and behold, the 0.48 becomes 4, the 0.6 becomes the 5, and there you go. That's the result we're working towards. Again, that question, or this part of the question, is nothing to do with integration, that's just to do with the setting up of the differential equation. It's part B that requires us to solve the differential equation, and we've got to find the value of t when h is 0.5, so how long after the tap has been running is the depth of water in the tank of 0.5 meters. So here we go. So there's our differential equation, and there we go. I've rearranged it so that we've separated the variables. So I've taken the dt over to one side, and I've brought the 4 minus 5h, the h over to the left. Now we can do the integrating. So integrating this one is a ln function, and again this 15 here is a combination of our constants 75, and the fact that when we integrate we're going to get a 1/5 coming to the front as a result of that 5 there. And again we've got the minus because we've got minus 5h, and on the right hand there's t plus c. When t was 0, the height of water in the tank was 0.2, so that's it, we were given that in the question. And so that gives us, when h is 0.2, put it into here, t equals 0, that gives us c equals minus 15 ln 3. So let's put that in there, and now I'm just going to do a little bit of rearranging and take that minus 15 ln 3 over to the other side. It becomes positive. So there we go, we've got an equation for t in terms of h, which is what we need. A little bit of tidying up in order to get that written as a single ln, and now the final step would be to put in when h is 0.5. There we go, t equals 15 ln 3 over 1.5, which is 15 ln 2, and there you go, there's your answer. Quite an involved question, two very distinct parts. The first, setting up the equation; the second, the solving the equation. The first one, chain rule; the second one, solving the differential equation via separating the variable and integrating. And there we go.